Good morning, everyone. Today I will be present a research paper titled "Dopamine, a peptide, strongly affects the phase behavior of lipid bilayers model." I will begin by summarizing the background and objective of the study, then walk you through the method, result, and the key conclusion. Let's get started. Let's start by looking at the background of this study. Misuse and overuse of antibiotics have caused more bacteria to become resistant. That means soon we will have no effective drugs against bacteria. Dopamine, a peptide used as a last resort against gram-positive bacteria, has already faced resistance strain in clinical setting. This means soon we may no longer be able to fight gram-positive bacteria. If this trend continues, we may reach a point where we can no longer fight gram-positive bacteria effectively. This later should imply the growth present in this background. Deliver or discover new peptides effective against gram-positive bacteria. But we face a problem. It is hard to find new peptides effective against gram-positive bacteria because scientists not entirely sure how dopamine kill bacteria. So, study how dopamine affects bacteria can help us learn how to find or make new antibiotics. Science is a challenge to develop new antibiotics. Understand how dopamine works is crucial. Uh, in this study, we use the advanced technology like fluorescence microscopy and AFS to investigate how dopamine impacts lipid bilayers. First, let me introduce the biology membrane model. A supporting lipid bilayer, solid supporting lipid bilayer, SLB. SLB is lipid layers supporting on a solid structure. There are three common methods for preparing this type of membrane model. First method is construct a hydrophilic part, and the next control a hydrophobic part. Use this method to construct SLP. And the second method is we can construct a lipid bilayer. It is a bulk, and the bulk is system. Break is system. It can attach the salt plate, and then can formation SLB. And then the third method, we can construct a half of SLB and prepare a solid plate, slender surface. And when his slender surface, it can bring in a half of SLB. And again, you can get SLB. In this work, second method was used to prepare the membrane. On the previous slide, I introduced the concepts of supporting lipid bilayer (SLB) and the three common methods to prepare them. Now I will focus on the SLB material and the preparation. We can see regions. Use four different lipids: POPE, POPC, POPG, and DMPG. In this work, we study two different membranes. Membrane 1 use POPE, POPE, POPG 3:1 to construct membrane 1. And the membrane 2, we use POPC and the DMPG 1:1 to construct membrane 2. And the SLB preparation, as we can It has 3 steps, one step and 2 steps to construct a ball. This ball is lipid bilayer and bracket is can attach the salt planar to formation SLB. After preparing the SLB, we need a tool to examine the membrane model in detail. For this purpose, we employed the atomic force microscopy (AFM). Let me explain how AFM works and why it's ideal for observe nanoscale change in biology membranes. The slide shows some AFM component. This is cantilever. The extent of cantilever deflection represents as delta z, can be adjusted by us. When the probe comes into contact with the surface of the object, the deflection change, known as cantilever displacement change. A laser is used to detect beam misalignment, which results in change in the intensity detected by the sensor. Finally, the feedback system informs a piezo scanner allows it to adjust the height of the stage of restore the initial difference level. Some detailed information in here. 1, 2, 3. Uh, uh, it can help you cleaner, and we can record this delta V to construct a height. Now that we have seen how AFM provides nanoscale mechanical, let's move on to fluorescence microscopy. This technology allows us to visually track the interaction of dopamine with specific lipid domains, thanks to its ability to highlight different components with fluorescence labels. Here is how it works and the key finding. Uh, first, we can see on the left slide of the project video, we see the basic component of a fluorescence microscopy. Very simple. On the right side of the projective video, show the SLB and the dopamine DAB how to observe fluorescence. When we see the computer screen, can see 2 different channels, TR and KYN. TR channel is receive transfer wavelength. KYN channel is receive dopamine wavelength. In previous study, we learned that dopamine with the PG lipid. We learned that dopamine in interaction with the PG lipid. Through this experiment design, we can better understand the difference observed in the image. This slide shows FN and AFN image of PPG. This SLB model is put to DAP as 20 degrees. In this temperature, PE is salt and PG is fluid because different lipid has different phase change temperature. We can see the picture A. Picture A, salt air is PE, salt, and the light air is PG, fluid. And we see the picture B. Picture B is KYN channel. We don't add dopamine. It's no signal. When we add 2 micromolar dopamine at different time, when we add the dopamine and show the different time at 180 seconds, we can find the 2 different channel has a signal, picture C, picture D, and we overlap it. We can find it's just the picture C is just like picture D. It's implying that the dopamine can interaction with PG. And we saw at 600 seconds, we can find the light air is increased and the dark air is decreased, and we overlap it. We can find the total air is increased, and we can see the AFA image. AFA image in the right, the dark color is PE, the dark color is PG fluid, and the light color is PE salt. When we add 4 micromolar dopamine, the salt air is increased and the flow air is decreased. AFA image further reveal that the salt domain grow and become fluid. This could be cause DAP group PG lipids together, changing the bilayer structure and properties, which might explain how it works against bacterial membranes. This slide shows AFA image and the height profile of the PEPG, this SLB model. We can see when we add the dopamine, it can change. It can cause the height change. You can see the right. The red line is at the dopamine. It can cause height change, and the black line is before at the dopamine. We then consider the influence of DAP on a specific aspect of the thermodynamic behavior of this model. This slide is Fn and the AFA image of PEPG, this SLB model, and 25 degrees exposed to 4 micromolar DAP. In this temperature, PE and PG are fluid. We can show the TR channel to see. In the TR channel, because PE and PG is fluid, so the signal is average. The average we don't see clear. And the picture E is in this condition AFA image. We didn't see difference. When we add 4 micromolar DAP, the TR channel and the K1 channel change. It's not average. We can see the dark air and the light air. It's implant that when implant that add DAP. DAP can cause cluster. This implant the DAP can interaction with PG, and we can overlap BC predat D to cleaner. Additionally, when we add 4 micromolar DAP, it can cause the height difference, the height increase in the FGH. And then we research the model 2. The slide shows is Fn image of this model 2 at 20 degree, and it's put to DAP. In this temperature, PC is fluid and the PG is salt. So we can see the picture A. Picture A, you can see the dark air. The dark air is PG, and the light air is PC. PC is fluid and the PG is salt. when we can see the A1 to E2, A1 to E2, when we A1 to E2 is at dopamine at different time, increase evolution time. So when we add the dopamine, the dark air, PG salt air, PG can decrease, can decrease. We can see this in B BEH 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 is a TR channel and the CFI is a dopamine channel. We can find the BH channel, the dark air is decreased, and the KYN channel CFI is increased. So the PG is decreased, and the dopamine interaction with PG is increased. It's increased. This slide show is AFN image of the Model 2 PC PG EBE SLB at 15 degree exposed to dopamine. The dark color is PG salt, and the light air is PC fluid, and we can find the finger-like structure and the boundary of the domain when the dopamine reveal the interaction of dopamine with the domain. This slide is force spectroscopy analysis and the AFA image of PG in this Model 2. Model 2 is put to increasing DAP concentration. The result we find the salt domain can decrease and the flow domain can increase when we increasing the DAP concentration. On the other hand, the PG salt domain, the air is decreased, become fluid, and the flow is decreased, can increase. There are two AFN images previous slide. Dark color is PG salt and the light air is PC fluid. We can see dopamine interaction with salt domain reduced by their sinks and the increased domain boundary. This study revealed less DAP interaction with phase-separate lipid bilayers, targets PG-rich domain and alternate layer phase state. In the Model 1, POPE, POPG 3:1, in fluid PG domain, DAP induce some air and increase salt region, and the Model 2, POPE, DMPG, EBE, in salt PG domain is called fluidification. This study used FFN and AFN to observe how DAP influence membrane model visually. Scientists need to conduct more research on dopamine to develop new antibiotics and save patients in terrible situations. Scientists must keep fighting.